Before we continue with the discussion of the mathematical formulation, I'll show you some slides on this polling, how to generate periodically domain reverse structures in lithium niobate. So, as I was mentioning to you, lithium niobate is a ferroelectric material, and the direction of polarization, there is a permanent polarization in the material. So, one takes a lithium niobate wafer, which is the plus is written there, that means the z-axis is pointing up, its optic axis is pointing up. And then, as I was telling you, one lithographically defines an electro pattern and then applies a high voltage, typically about, as is written here, 11 kilowatts and 500 micrometers. Okay, so that's 22 kilowatts per millimeter. The breakdown strength is much higher. So what happens is, where the electric fields are applied, the domains switch from vertically up to vertically down. So you get a periodic polling of the crystal, and you can actually have more complex electrode structures to achieve this. So for example, let me show you the top surface of the substrate after polling. And what happens is, you can actually show the polling by etching. The Z plus and Z minus surfaces get etched at different rates. So this structure that you see is actually the periodically poled substrate with this in one of them, and the other one is the Z minus, Z plus, Z minus, Z plus. It's periodic, and you can see it's very clearly periodic with a certain period, and the propagation direction is like this, vertical, perpendicular. So these domains are like this, and you're propagating perpendicular to the domains. So you get a periodic polling, which is possible in lithium niobate by periodically applying electric fields, and so this is now a standard technique which is used to pole crystals of lithium niobate. Let me show you some examples of high efficiency generation in using periodically poled substrates. Here is a report from a journal in Optics Express, which is a journal published by the Optical Society of America, and you can see here for about 25 watts of fundamental power, you can generate something like 3 watts of second harmonic power. So that's a good efficiency, and as you can see, that shows the change of the fundamental power versus the second harmonic power versus fundamental power, and this is just to show you that you can achieve very high efficiencies by using periodically poled crystals. In fact, in a recent publication in 2009 June, they have actually shown you can generate green light using this second harmonic generation. In fact, there are some laser pointers, green laser pointers. They have actually a red laser, a second harmonic generator within the green laser pointer. So you can actually convert 808 nanometers to 404 nanometers. Actually, it's okay. 808 nanometers is used to pump a neodymium YVO4 crystal that generates 1064 nanometer. The 1064 nanometer then is converted to 532 nanometers using a magnesium oxide doped lithium niobate crystal. And you can see the powers coming out at the green, 11 watts. The argon laser, which is a huge laser in the laboratory, that generates a few watts of power. So that's a huge power, and these are now being seen for application for laser displays. You need to have the 3 primary colors, and this is one of the primary colors, the green laser. Let me show you some interesting configurations you can do by making crystals with multi-periods. So you have one period, then second period, third period. So depending on which period you use, you can achieve phase matching for different frequencies. Because remember, the phase matching period depends on the frequency of the fundamental wave. So you can actually make a crystal with multiple periods and use these multiple periods to achieve phase matching at different fundamental frequencies, or you can actually fan the grating like this. So depending on the vertical position where you're coming, the period that will be encountered by the light will be different. So you can achieve tunable phase matching essentially. So you can actually move the crystal, and depending on where you are focusing the laser beam, you can have different phase matching conditions satisfied. You can have chirped, where the spatial period is changing with position. You can have superstructure. So there is one period which is the internal period, and then there is another period which is this is being repeated again and again. The super period gratings. So you can actually do a lot of interesting engineering to achieve different functions, multifunctional. As you will see later on, for different frequency generation, the periods are different. So you can do second harmonic generation and then different frequency generation, etc. In a single crystal. So here's an example of how in a single crystal you launch 1064 nanometer light, use optical parametric generation to generate a new frequency, then use second harmonic generation and third harmonic generation to generate multiple wavelengths simultaneously. This is a single crystal in which you generate multiple domains of different periods. Each period is meant to achieve different nonlinear effects essentially. So finally you can generate all the three primary colors. So there's a lot of activity in using this nonlinear interactions to achieve new wavelengths which are otherwise not possible because conventional lasers have fixed wavelengths which are emitted by the laser. You can actually do more interesting things of compressing a pulse when it generates a second harmonic. And so here is a very interesting period paper in which you have a period varying from 6.5 to 1.8 microns, and that you can show is actually a fundamental wave comes in with a duration of 8.6 femtoseconds, and it gets compressed in the second harmonic to about 6 femtoseconds. So you can do a lot of things that is by essentially engineering the domains of the crystal, which is not possible if you have birefringent phase matching. So quasi phase matching gives you a lot of flexibility in achieving multifunctionalities. Yeah.
So in the figure that you showed that different colors were generated.
Yeah.
3 colors were generated.
Yeah.
So here what happens is that first the incident wave comes and its second harmonic is let's say generated. Then that second harmonic of that second harmonic is generated.
No. You are putting in 1064 nanometers.
Yes.
You're also putting at 1430 nanometers. So it generates a difference frequency. That is optical parametric generation. So we will discuss this difference frequency generation a little later. Then there is the second harmonic of 1064 is 532 nanometers, which comes out. Then the 1430 and 1064 mix to generate a sum frequency generation at 611 nanometers. And then you have a 4676 nanometers coming from the 1430 nanometer. So you have actually multiple processes, nonlinear processes, all depending on chi2. Because remember, chi2 process can be second harmonic, sum frequency, difference frequency. So the generated frequency is so powerful now. It's not very low power. Now the efficiency is just quite high that you can use the generated light to further undergo further nonlinear processes for which you require different periods. And so the periods can be different at different positions of the crystal to compensate for the phase mismatch for that interaction process.
Is it possible that the efficiency for second harmonic generation is that high? I mean, if you use chirp gratings, these chirp periods, then is it possible that the efficiency for the first second harmonic generation is so high that further we can use a period that second harmonic of that second harmonic can be generated? I mean, the efficiency can.
No, that is not chirp. I will have to generate two different gratings. One grating for fundamental second harmonic, another grating from second harmonic to the fourth harmonic of the fundamental.
So
2 omega to 4 omega.
We cannot do it in one.
No, because the periods required are very different. One period depends on n omega and n2 omega. The other depends on n2 omega and n4 omega. And because of strong dispersion, as you go to the lower frequencies, as you go to higher frequencies, the periods required may be very different. You can't chirp it so much. There's no point in chirping, because chirping I need for it to extend in the bandwidth of the interaction process.
Okay.
But otherwise, I know the period to convert from lambda 1 to lambda 2. or omega 1 to 2 omega, omega to 2 omega. Once I convert to omega to 2 omega, then I put another period to 2 omega to 4 omega. So you will set in omega and out will come 4 omega. You don't care what is happening inside. So it is possible in general to have multiple processes taking place simultaneously.
The point was that we can insulate a light which is at a given frequency,
Yes.
at a lower frequency,
Yeah.
which is on the lower end of the visible light. So,
Okay.
So we can generate 2 omega from that,
Okay.
and then we can generate 4 omega from that. So we can reach from violet to red.
Yeah.
In that process. So using
No, the other way around, red to violet. Yeah.
Red to violet.
Yeah.
In only one input.
Sure. That's what I said. Yes, it's possible. It's possible to go from omega to 4 omega by going from omega to 2 omega and then 2 omega to 4 omega.
Take out some output from the 2 omega also.
Sure. It's coming out here. 532 is coming out here. And 532 which is generated can also be mixed with other wavelengths at the input to generate new wavelengths. For that, I need to calculate what is the QPM required, period required, and I need to make that period in my crystal. Okay, so what we will now do is continue our discussion on the second harmonic generation that we were doing the other day. We were actually discussing the situation where the efficiency could be very high. That means when I don't neglect the pump depletion. Remember, we started with these equations. dE1 by dz is equal to I omega d by Cn1 E2 E1 star, and dE2 by dz is equal to I omega d by Cn2 E1 square. So I am assuming delta k is equal to 0. I am assuming delta k is equal to 0. Blackboard. Can you see here?
Yes, sir.
Anyway, let me write it. I forgot a switch. Is that the maximum brightness? Can you see?
Yes, sir.
Okay. Okay, so we had assumed delta k is equal to 0. Phase mismatch is equal to 0. And let me call this coefficient as kappa. So because delta k is equal to 0, n1 is equal to n2. And let me call this as kappa is equal to omega d by Cn1. So what we did was, we substituted E1 of z is equal to U1 exponential I phi 1, E2 is equal to U2 e to the power I phi 2 into these two equations. Then where U1 and U2 and phi 1 and phi 2 are all real quantities, we then equated the real and imaginary parts on both sides and got the following four equations. Let me rub these equations. So what we got was du1 by dz is equal to minus kappa u1 u2 sin theta. du2 by dz is equal to kappa u1 square sin theta. u1 d phi 1 by dz is equal to kappa u1 u2 cos theta, and u2 d phi 2 by dz is equal to kappa u1 square cos theta, where theta was defined as phi 2 minus 2 phi 1. So what I do is I substitute the complex fields E1 and E2, which I write as U1 times exponential I phi 1 and U2 times exponential I phi 2, substitute into those equations and equate the real and imaginary parts on both sides, and I get, instead of two complex equations, I get four real equations now. Now, what I will do is, I can actually solve these equations by the following procedure. So, let me calculate d theta by dz. This will be equal to d phi 2 by dz minus 2 d phi 1 by dz. Theta is phi 2 minus 2 phi 1. So, I substitute for d phi 2 by dz and d phi 1 by dz from here. So, this is equal to kappa u1 square by u2 cos theta minus 2 kappa u2 cos theta. So, this is equal to kappa cos theta into u1 square by u2 minus 2u2. So, it's a mathematical trick that I am going to do to just solve these equations. So, I get d theta by dz is so much. Now, let me calculate. So, I will, okay, you can also calculate d by dz of log u1 square u2. This can be calculated. This will be in terms of, so this is actually 1 by u1 square u2 into u1 square du2 by dz plus 2u1 u2 du1 by dz. And I have expressions for du1 by dz and du2 by dz here, which I can substitute here. And this is simple exercise. You can show that this is actually happens to be equal to minus d by dz of log cos theta. So, if you substitute for du2 by dz and du1 by dz here, you will see that the right hand side is essentially related to d cos theta by dz. So, this equation. So, this is actually minus 1 by cos theta into minus sin theta d theta by dz. So, if you expand this, you will get in terms of d theta by dz, you can use this equation and show that these two are equal, which implies essentially that d by dz of, so if I bring it to the left hand side, I will get d by dz of log u1 square u2 plus log cos theta is equal to 0. So, what does it imply? Log of u1 square u2 cos theta is equal to 0. So, this implies u1 square u2 cos theta is a constant of motion independent of z. As the waves propagate, u1 and u2 and theta everything changes, but u1 square u2 cos theta remains constant. It's just simply simple mathematical equation that I am using to get this condition. Now you note that for the case of second harmonic generation, what is the initial condition? I have only the fundamental incident on the crystal. So, at z is equal to 0, E2 of z is equal to 0. There's no second harmonic incident. So, I have a crystal in which I launch wave at omega frequency. So, this implies u2 is equal to 0 because E2 is u2 times exponential I phi 2, and u2 is equal to 0 implies C must be 0 because this is a constant of motion. So, at z is equal to 0 also it is valid. So, at z is equal to 0 I have u1 square of 0, u2 of 0, cos theta of 0, and because u2 of 0 is 0, the constant is 0, and as that changes, u1 will change, u2 will change. So, how will I maintain this equation? Theta has to be, cos theta must be 0, which means theta must be plus minus pi by 2. So, theta will become, and And remember, theta is phi 2 minus 2 phi 1. Yeah.
Then we have taken that n1 equals to n2.
Yeah, phase matched. We are solving this equation only under phase matching. Okay, it's possible to solve in the original paper by Armstrong. I'll give you the reference. In 1962, Physical Review A, this equation is solved in more general terms, which in terms of elliptic integrals and so on. So I'm not going to those details, but I just want to show you that it is possible to solve this equation when you have phase match situation. It's much easier. Okay, so delta k is equal to 0. I get those two equations, and then I'm trying to solve this equation under this condition, delta k is equal to 0. So once theta becomes defined like this, these two equations will give me now, these two equations get simplified to the following two equations. So du1 by dz, let me assume theta is equal to plus pi by 2. I leave the problem to you to do for theta is equal to minus pi by 2. For theta is equal to plus pi by 2 minus kappa u1 u2 and du2 by dz is equal to kappa u1 square. Sin theta becomes 1. Now, again I want to leave for you to show these equations satisfy the following condition: d by dz of u1 square plus. What is this equation? Energy conservation. Please remember, this is under n1 is equal to n2. Otherwise, we will have n1 mod e1 square by 2c mu 0 plus n2 by 2c mu 0 mod e2 square must be constant. Right? Because n1 is equal to n2, it simply becomes e1 square of e2 square or u1 square of u2 square. So this implies u1 square of z plus u2 square of z must be equal to u1 square of 0. Because at z is equal to 0, there is no second harmonic incident. I am assuming that the crystal, there is only fundamental wave incident in the crystal. So let me call this u1 0. So I need to solve this equation. So u1 square becomes u1 0 square minus u2 square. And so this equation simplifies to du2 by dz kappa times u1 0 square minus so I can actually integrate this equation. I will have integral du2 by u1 0 square minus u2 square is equal to integral kappa dz from 0 to z from u2 is 0 to some u2. At z is equal to 0, u2 is 0. At z is z, the value of u2 is so much. That's an integral function. Okay? So I'll give you the solution. The solution comes out to be u2 of z is equal to tan hyperbolic function. You can actually integrate this equation by transforming variables and show that the solution of that equation, that integral, is in terms of tan hyperbolic inverse, and so you get this expression for u2 of z. From here you can calculate p2 of z is equal to n2 by 2c mu 0 u2 square into area. n2 by 2c mu 0 mod e2 square into area. Mod e2 square is u2 square into area. So u2 square is given here, and N1 is equal to N2. So this you can show again that this is P1 of 0 tan hyperbolic square of you can okay, this is actually square root of 2c mu 0 P1 0 by N1 into area into. I've replaced U10 by the power in the fundamental, and kappa is a known quantity omega d by c N1. So the power in the second harmonic grows with z like this. And if you all know, tan hyperbolic square function is a monotonically increasing function. So from z is equal to, if you plot as a function of z, it will go like this. The maximum power you can get is P1 0. This is P2 of z versus z. Now I leave the following problem, that if the efficiency is small, then you can convert the tan hyperbolic function into, so if the efficiency is small, that means P2z must be very, very small. That means this argument must be small. Then you can express the tan hyperbolic function in terms of the argument. And I would like you to show that the efficiency comes out to be exactly what you have calculated before under the no bound depletion approximation. That means here, the expression which we calculated will go like this. It will be overlapping with this variation until about a efficiency of a few, maybe 5-6% or 10%, and then it will diverge up because it increases quadratically with z. The increase is not quadratic, it's in the form of tan hyperbolic function. So, two things I want you to show. First thing is, for low efficiencies, P2 of z, okay, for low efficiencies, eta same as before. And the second thing I want you to calculate is P1 of z. This is the power in the second harmonic. What is the corresponding power in the fundamental as z increases? Note that in this calculation, you can never convert all the power from the fundamental to second harmonic. Because it is a tan hyperbolic function, it asymptotically approaches P10. It's not a periodic exchange between omega and 2 omega. So omega, you launch omega, you generate 2 omega, continue to generate 2 omega, and the 2 omega power keeps on increasing. And if you are perfectly phase matched, it actually approaches the full efficiency of 100% at essentially infinite lengths.
So what is the dotted curve?
This dotted curve is the for low efficiencies. What we had calculated, sine square delta k z by 2 by delta k by 2 whole square in terms of that function. So we had actually calculated earlier P2 of z, assuming E2 was a constant. E1 was a constant. Assuming E1 was a constant. So on that approximation, efficiency will be low, and this, the low efficiency expression, and this match for low efficiencies. For higher efficiencies, that equation cannot be used. And actually equation is this, and the efficiency goes to 100% as you increase the length of interaction. Okay, so now let's look at another problem, and that is, as I was mentioning to you before, generation of omega from 2 omega. So what we have discussed is, I have a crystal, I launch omega, and I generate 2 omega. Second harmonic generation. So for this delta k is equal to 0. Now I take the same crystal and I launch 2 omega. Can I generate omega? The subharmonic generation. Remember we have two equations, dE1 by dz and dE2 by dz. We solved the dE2 by dz equation under no pump depletion approximation and got a variation of we got a certain efficiency, and we got an efficiency for complete conversion, for where you don't neglect the depletion. Can I reverse the problem and I say I launch 2 omega and I want to generate omega? So here what is happening is 2 photons at frequency omega merge to form 1 photon at frequency 2 omega. Here 1 photon at 2 omega is supposed to split into 2 photons at frequency omega. This is also called parametric down conversion. You are decreasing the frequency, you are generating a lower frequency from a higher frequency. It's called parametric down conversion. And in fact, this 2 omega can be written as a sum of an infinite sets of 2 frequencies. 2 omega is omega plus omega. 2 omega is omega 1 plus omega 2. Sum omega 1 plus omega 2 is also 2 omega. So in fact, there are infinite combinations of this equation. Of course, you need to satisfy phase matching condition to generate the new frequencies. So we will go to this a little later, but first thing I want to address the problem is, if I launch only 2 omega, can I generate omega? So let me go back to those equations. And let me assume no pump depletion approximation, which means I assume E2 is a constant. Right? So the equation which I need to solve now is this first equation. I omega d by Cn1 with the condition that E2 of z constant and E1 of 0 that means I have at the input of the crystal a second harmonic with a certain electric field amplitude E2 and no incidence of any fundamental wave. There is no omega incident, there is only 2 omega incident. In the first case, there was only omega incident, there was no 2 omega incident. I generated 2 omega from omega. Now I'm trying to generate omega from 2 omega by launching only 2 omega.
Here E2 represents 2 omega and E1 represents omega.
Yeah. I continue to represent the second harmonic by the electric field E2, the fundamental by this electric field E1. Now first thing you already notice here that if E1 of 0 is 0, dE1 by dz at z is equal to 0 is also 0. This equation, because this is proportional to E1 star. So what do you expect? It will continue to stay 0. Let me calculate. So let me differentiate this equation. D square E1 by dz square is equal to I omega d by Cn1 E2 d E1 star by dz dE1 star by dz I substitute from here. So I omega d by Cn1 E2 into minus I omega d by Cn1 E2 star E1. Which is equal to omega square d square by C square N1 square mod E2 square into E1. Now let me call this gamma square is omega square d square by C square N1 square into mod E2 square. So this equation is simply d square E1 by dz square is equal to gamma square E1. What is the solution? E1 of z is equal to, or in terms of hyperbolic functions, right? So what will it be? A sine hyperbolic gamma z plus b cos hyperbolic gamma z. Because E1 of 0 is 0, what should be 0? Because E1 of 0 is 0, constant b must be 0. Because E1 of 0 is 0 plus b. So b is 0. b E1 by dz is also 0 and z is equal to 0. That means a is also 0. So E1 of z, so this gives me b is equal to 0 because E1 of 0 is 0 and a is equal to 0 because b E1 by dz is 0 at z is equal to 0. So E1 of z is equal to 0. No generation of subharmonic. Omega can get converted into omega. Those equations predict. But those same equations tell me that I cannot convert 2 omega to omega. There is nonlinearity. There is nonlinear effects. The powers are large. There are strong electric fields, but no generation of omega. When I do an experiment, I find omega. And the explanation is purely quantum mechanical. Note that according to quantum mechanics, I cannot have complete vacuum in terms of no electric fields and no magnetic fields. I cannot have a situation where the electromagnetic energy is 0. There's always 0 point energy, 0 point fluctuations, and it is those 0 point fluctuations which will induce the second harmonic to downconvert. For example, if I don't put this condition, and if I assume a finite electric field to be incident at frequency omega, I can solve this equation because then both of them don't become 0. And I will get a solution to the problem. Let me try to analyze, for example. So let me assume that instead of this, so first thing is that without this noise, without this quantum noise, there is no subharmonic generation. I cannot generate omega from 2 omega. I cannot generate, this is called, what is called as spontaneous parametric fluorescence or spontaneous parametric downconversion, SPDC. It's a spontaneous process in which the 2 omega photons spontaneously split into 2 omega photons. It is parametric downconversion. It's a downconversion process because it goes from a higher frequency to a lower frequency. And spontaneously it has to happen. So SPDC, the spontaneous parametric downconversion, has a completely quantum mechanical origin. And this situation is called degenerate parametric fluorescence because the two frequencies which are coming out are the same. I can split a 2 omega photon into 2 different frequency photons whose sum of frequency is equal to 2 omega. So that will be non-degenerate parametric fluorescence. This is called degenerate parametric fluorescence. Degenerate means the output 2 photons have the same frequency. The equation we have derived is only for degenerate because we have only considered 2 frequencies, omega and 2 omega, in the process. After we finish second harmonic generation and this discussion, we will go into a more general case where I can have 3 frequencies interacting with each other. And that will be used for understanding more things about parametric processes. Now, let me try to show you mathematically some very interesting features of this equations.
Sir,
Yeah.
are you saying that we're going to use these same equations to prove that it's possible to generate omega from 2 omega?
No. We have to go, when we go to quantum mechanical description, then only I can show you. But these equations can be used when E1 0 is not equal to 0. That means in addition to 2 omega, if I put a small omega here.
So, but isn't this similar to the condition when omega 1 got when the electric field at omega got depleted and there was a certain.
Exactly. So it's in between condition. I launch omega in the case. After some distance, I have both omega and 2 omega.
So, but according to our equation, the energy only gets pumped into E2, not and from E1. There's no.
You're right. But I will show you that depending on the phase difference between these two waves, energy can move from omega to 2 omega or from 2 omega to omega.
What was the difference in the first case that we did where energy was only traveling?
Because that phase difference never appeared. Here I will show you, depending on the phase difference between these two waves, I can either go from omega to omega or 2 omega to omega. Yeah.
You said that quantum mechanically electromagnetic energy can never be zero. You said
Yeah.
that.
You cannot have a situation where electric and magnetic fields are zero.
If they're finite, so how can we know that there must be some component at frequency omega present such that subharmonics are generated?
Because they are present at all frequencies. In free space, all frequencies are allowed, and so there is fluctuations corresponding to all frequencies. If you take a cavity, the cavity only allows certain frequencies of oscillation, and then noise is present at those frequencies. The other frequencies cannot exist anywhere inside the cavity. I mean, in theory, assuming that these frequencies are very well defined and individual frequencies. So this situation is where I have a strong 2 omega beam and a weak omega beam coming in. This is very weak, but not zero. So let me solve this equation. So what is the expression I will get now? So let me call this, this is not zero. So I call this, let me write here again. E1 of 0 is E1 0. So I get B is equal to E1 0 from here. So dE1 by dZ is equal to A gamma cos hyperbolic gamma Z plus gamma E1 0 sin hyperbolic gamma Z. So dE1 by dZ at Z is equal to 0 is equal to A gamma is equal to I omega d by Cn2, Cn1 into E2 of 0, E1 star of 0. I am substituting the expression for dE1 by dZ, that is I omega d by Cn1, E2 E1 star. So let me assume that E2 of 0 is U2 e to the power I phi 2 and E1 of 0 is U1 phi 2 0 and exponential I phi 1 0.
This is sine or sine hyperbolic?
Sine hyperbolic, sorry, I'm sorry. Yeah, sine hyperbolic. Okay, so I get an expression for A. A is equal to I omega d by Cn1. Remember, I had called this kappa. So kappa by gamma U2 U1 U2. This is let me mixing up too many symbols. So let me call this. This is E1 0 actually, because E1 of 0 is E1 0. Okay, this is complex. Please just correct this. This is E1 0. U1 0 e to the power I phi 1 0. Amplitude and phase. So this is B is equal to U1 0 e to the power I phi 1 0. And this is actually gamma the second harmonic is constant, so there is no z dependence on the E2. So this is A is equal to I kappa U2 U10 exponential I phi 2 0 minus phi 1 0 minus phi 1 0. Because you have an E10 star. E10 star is U10 exponential minus I phi 1 0. And so that's the expression for A. So let me substitute into the solutions, and I get the complete solution as so let me write this first one first. So what was E1 of Z? A sine hyperbolic gamma Z plus B cos hyperbolic gamma Z. So A is I kappa U2 by gamma U10 exponential I phi 2 0 minus phi 1 0 sine hyperbolic gamma Z plus U10 e to the power I phi 1 0 cos hyperbolic. And substituting the values of A and B. So I can write this as E1 of Z. Let me take this common. Now remember, what was gamma square? Gamma square was omega square d square by c square n1 square mod E2 square. This is equal to kappa square into U2 square. I defined gamma square as omega square d square by c square n1 square into mod E2 square. Omega d by c n1 is kappa and mod E2 square is U2 square. So kappa times U2 is equal to gamma. So these cancelled off. And I write this as U10 exponential I phi 1 0 into cos hyperbolic gamma Z plus exponential I have I phi 2 0 minus 2 phi 1 0 plus pi by 2. The I factor multiplying here I have written as exponential I pi by 2, and then I have sine hyperbolic gamma Z. What I have done is I have used the initial conditions at Z is equal to 0 to calculate the two constants A and B, substituted into the solution and express the solution like this. Now you see E1 Z is not 0. Now I can have two situations. Suppose this coefficient, suppose phi 2 0 minus 2 phi 0 2 phi 1 0 plus pi by 2 was equal to 0. The initial phase of the fundamental, initial phase of the second harmonic. Remember, what is phi 2 0? E2 0 was U2 0 exponential I phi 2 0. This is the phase of the second harmonic 2 omega wave at the input. This is the wave of the fundamental wave at the input, the phase of the fundamental wave. Suppose I could satisfy this condition, what will happen to E1 of Z? What happens to this sum? This becomes, exponential becomes 1, sum of cos hyperbolic and sine hyperbolic. It becomes exponential gamma Z. Cos hyperbolic x plus sine hyperbolic x is exponential x. Cos hyperbolic x minus sine hyperbolic x is exponential minus x. If I had, this is one case, so if I had phi 2 0 minus 2 phi 1 0 plus pi by 2 is equal to pi, or pi, then E10 will be E1z will be U10 e to the power I 510. If I choose this exponential factor to be, this phase to be pi by minus pi by 2, so this is 0. If this happens to be 0, that is 520 minus 2510 is minus pi by 2. Then the fundamental wave grows exponentially. This is assuming no pump depletion. That means I'm solving the equation assuming E2 is a constant. So there is an exponential growth, but you cannot extend this to large values of z. Okay, so the omega frequency grows exponentially. If you choose this phase of 520 minus 2510 is minus pi by plus pi by 2, if this difference is plus pi by 2, then the fundamental decrease. And this decay, which means that the energy is transferring from omega to 2 omega here, and here it is transferring from 2 omega to omega. What is this? Amplification. U10 was the input field at the omega frequency. As that increases, the omega frequency keeps on increasing in amplitude. This is an optical amplifier. This is called an optical parametric amplifier. It uses the nonlinear property to amplify the signal. And the interesting thing is, this amplifier depends on the phase of the input signal. If your input signal phase 510 satisfies this condition, the signal will get amplified. If the input signal phase satisfies this condition, it will get de-amplified. This is not like laser amplifiers. If you take a laser amplifier, irrespective of what you do to the input phase, it's always amplified. It uses population inversion. This uses a different principle completely. It uses a nonlinear effect, and this is called a parametric amplifier, and this is a phase sensitive parametric amplifier. Later on I will show you the parametric amplifier can operate in phase sensitive fashion or phase insensitive fashion, and you can use the phase sensitive nature of this amplification process to do very interesting features in generating light with noise properties which are better than what you can achieve with lasers. You can use this process to what is called a squeezed vacuum. You generate squeezed vacuum. Vacuum has certain fluctuations. You can reduce the fluctuations below what standard vacuum has by using this kind of a process. And that's called squeeze vacuum, and squeezing is a very important technique that is used today to reduce the noise of signals, and this is used in many applications, including in gravitational wave observatory, for example. There is a LIGO interferometer which is being built to detect gravitational waves. So you need waves whose noise levels are very, very low. And so the squeezed light which comes out from this kind of a process can be used for applications where you want very low noise signals. Okay, we can't have the quiz now. Okay, so there is a very interesting feature here. So let me show you some slides before I stop. So we'll have the quiz maybe on Thursday itself. So this is a very interesting feature of an amplifier which does not use population inversion, but which uses nonlinear effects, and the amplifier is phase sensitive. So we'll come back to this phase sensitive amplifiers a little later, but let me finish the lecture by showing you some slides. Okay, so this is what is called parametric fluorescence. This is the degenerate parametric fluorescence where photons at 2 omega split into 2 photons at omega, and these 2 photons which are coming out actually are generated from the same photon, 2 omega, and they can possess certain peculiar features of what are called as entanglement, properties of entanglement. So there are correlations between these 2 photons which are beyond what classical physics predicts. And this process is very much used in quantum information science. So here is a typical example of light being pumped at 655 nanometers, and out comes light at longer wavelengths, which is down conversion. And depending on the quasi-phase matching period, the pairs of light wavelengths coming out are such that the omega 1 plus omega 2 is equal to the omega of the instant light. 655 nanometer photons are splitting into two photons of lower frequencies or higher wavelengths, and the sum of these two frequencies is equal to 655. The sum of these two is also 655, but in this case, these are coming out because you satisfy the phase matching condition for that pair of frequencies. So if you change the period of this quasi-phase matching, you can generate different pairs of photons which are coming out. Please note the power levels, femtowatts, very, very low generation powers. These are, this is called fluorescence, parametric fluorescence. You shine light at this wavelength and out comes light at new wavelengths, which are longer wavelengths than the input light. What we discussed today is a parametric amplifier. You can amplify an input signal, and this is phase sensitive. So it has very interesting quantum properties, which we will come back when we discuss quantum mechanics. At that time, I will bring back this problem and we'll look at some quantum properties of this. Incidentally, parametric amplifiers were investigated by Michael Faraday in 1831. So you take a wine, if you rub your fingers on a wine glass, the wine started to vibrate. And he found out that there were two complete vibrations of the support for one vibration of the liquid. 2 omega omega. Okay? Many of you may not have done this experiment. Meld this experiment where you can excite a string into oscillation by forcing it at twice the frequency. And Lord Rayleigh has analyzed this. And let me show you a classic example of a child on a swing. This child sits, then stands up, again sits back, and stands up. Two frequencies of the child sitting and standing for one period of the swing. The child is pumping the swing at 2 omega. And the swing is oscillating at omega frequency. And so also note that the child has to pump the swing at the right phase. If it gets out of phase, the swing will come down to rest. And also, nobody needs to push. The child can generate some noise in the swing and then start to amplify that. But then the moment it starts to swing a little bit, you sit and stand at the right time, the right phase, and you start to amplify the signal. So you can actually generate from noise, amplify that noise, and generate the oscillation. And here is some experimental results showing how the amplification depends on the relative phase, which is what these equations predict. And you can, these are some experimental results showing phase-sensitive amplifiers. And so these are very interesting. So there is a lot of work going on in phase-sensitive amplifiers. And as I said, one of the most interesting applications of this is in quantum noise reduction or generating non-classical states of light and so on. Okay, thank you.